Hey there, welcome to Pomodoro Joe for Thursday, October 26th, 2023. Today we're looking at LeetCode problem 823, binary trees with factors. This is a medium problem. Given an array of unique integers, array, where each integer, array index I, is strictly greater than 1. We make a binary tree using these integers, and each number may be used any number of times. Each non-leaf node's value should be equal to the product of the values of its children. Return the number of binary trees we can make. The answer may be too large, so return the answer modulo 10 to the 9th plus 7. All right, so let's break this down a little bit. Basically, we're given an array of integers. Now, the integers are unique, but we can use them multiple times. And our goal is to return the number of binary trees we can make using those integers. Now, the rule with making our binary tree is that every node, which will be the value of some integer in our array, its value must be the product of its children's values. So its left node times its right node values. All right, so let's take a look at the example here. We've got 2 and 4. So we could have one tree that's just 2, another tree that's just 4. Then if we had a tree that's node was 2, could it have any children? Well, we don't have two values that we can multiply to get 2, so 2 can never have any children. Now 4, it could have children. It could have a left that's a 2 and a right that's a 2. So that gives us 3 options, I guess. So we've got 2 as a standalone tree, 4 as a standalone tree, and then 4 with 2 children of a left and right, both equal to 2. So that's this here. All right. 2, 4, 5, 10, kind of similar thing. 2 can't have any children, but it could be its own tree. 4 could be its own tree, or it could have children of 2. 5 could be its own tree. Now there's nothing that we can multiply to get to 5, so 5 will never have any children either. But 10 could have children. 10 could be 2 times 5 or 5 times 2, so I guess you have 2 options there. And I think that might be it. So that gives us 1, 2, 3, 4. And then another one 5 here, and then 6, 7, because 10 can have a 5 and a 2, or a 2 and a 5. It's reversible. All right, so this seems pretty straightforward. We'll put 25 minutes on the Pomodoro timer, and we will get started. Now for this one, I think I'll go the simple route. We're just gonna do this recursively. Now this won't be super fast, but it's simple to understand, and then you can always optimize later. So let's create an internal recursive function here. And we'll just call it nums vector binary trees recurse. All right, and for this one, I'm just going to take the root. So the plan here is just to have this function where we can pass in a root. So we'll assume that every number in our list could be the root of a binary tree. And then this function will calculate, well, how many different variations of trees can we create with this number as the root? All right. So for now, I'm just going to pass. Okay, then out here, we'll have some result. We'll set it equal to 0. And we'll return our result at the end. And for this, we're just going to go through every single number in our array and ask, if this number were the root, how many different trees could we create? So for every number in our array, our result will increase by this number factored binary tree recurse with this number as our root. And then at the very end, we return our result. Now we do need to do this return result of 10 to the 9th plus 7, so let's actually create a helper out here. We'll have our mod value, and this is just going to equal 10 to the 9th plus 7. And at the end, we will just return our result, mod, our mod value. Okay, so this is our main driver right here. But now we still have to implement our function. Okay, so now let's get to our recursive function. All right, anytime we have a recursive function, we'll need to come up with a base case. So what are our base cases here? Well, one base case is, let's say we don't have a root. So if not root, we'll just return 0. Now, I don't really think we'll run into this base case because we're guaranteed. It said something about it being greater than 1. Yeah, strictly greater than 1. So we'll always have something that we're passing in, but it's still one base case we could cover. All right, so now that we've got this base case, although again, I don't think we'll really run into this base case, let's go on to our recursive cases. So for this one, we'll assume that this root is going to be the root of our tree. Now we need to find factors or other numbers in our array that when multiplied together, they equal our root. Okay, so for every number in our array, I guess we can check a couple things. First, if this number is greater than or equal to our root, we know that it cannot be one of our children because there's nothing we can multiply that number by that will equal our root. So if this number is greater than or equal to a root, we'll just continue. There's nothing we can do with that number. All right, what else can we do? Well, next we can see what's our other factor here. So let's assume that this number is our left. Let's do it this way. So if left tree, or our left child, is n, then our right child has to equal, let's see, that's going to be our root divided by this n. Now I'm doing an integer divide here. Now there's a couple things that could happen. Let's say our root is 5 and n is 2. We can divide 5 by 2, but that doesn't really give us a valid right. It gives us something that's not really an integer. So I guess we could actually avoid that. We could actually just do this divide directly. We might end up with a floating point number, but our next check will sort of weed this out because our number, this right, has to be in our array. Now we already know the left is in the array because we're getting it out of the array, but this right number also has to be in our array to be a valid child. So we can check if right is not in the array, then it's not a valid child and we can continue. All right, so continue just means exit out of the loop and go back to this check. So we're just going to exit back and go up to this 4. All right, so we'll early out if our number is already greater than or equal to our root because its children have to be less than the root themselves. And we'll also exit out if this right number is not in the array. So we'll grab our left number, check to see what the right number has to be in order for these two children to multiply together to equal our root, and then we'll exit out if this right is not in the array. Okay, what's next? Well, now we have a left and a right, and when they're multiplied together, they should equal our root. So this should be a valid tree, or one valid tree. But then we need to check those children to see how many different variations of trees they can be the root of. So this is just the starting point of 2 child trees, and we can use those child trees and basically multiply them together. So if the left has 10 variations and the right has 10 variations, that means between the two, we've got 100 different variations of trees that we can create, because we can take every tree on the left and we can basically have every variation of tree on the right. So that's 10 times 10. Okay, so for this, let's just have a left count here. How many different trees can we create with this left node as the root? Well, we'll just use our recursive function for that. So we'll call this recursive function and we'll pass in the left node. And then we'll do the same on the right. What's our right count? How many different trees can we create with this right number as the root? Awesome. All right, now that we have this, our total count, that's going to equal the left count times the right count. All right, and now we can increase our result by this total count. So our result plus equals total count. All right, now I don't actually have my result declared, so I'll want to do that out here somewhere. Let's do that up here. So our result, let's see, we'll start that at 1, because if we made it past this check, we know we have some root node, and we know it must have come from our array, otherwise we wouldn't have passed it in here. And so that root node can always just be a node on its own. So our result can always have at least 1 tree. Okay. All right. Now we get into some tricky business. So we could, after this whole loop, we can just return our result. And we'll actually do the mod here just to make it a little bit faster. So mod val. But there's one thing I haven't accounted for. and that's illustrated by this first example here. This 4 can have a left child of 2 and a right child of 2. But if you swap them, left and right, it's still a left child of 2 and a right child of 2. So that's not 2 unique trees, that's only 1 tree. So if our left node and our right node happen to be the same, then we don't want to double count. We can't actually reverse our trees or mirror our trees. So in this case, we're only counting them once. But if they're not the same, we can actually flip them and mirror the trees, the left child and the right child, and actually double the number of trees that we can create. But that's only if the left and the right are not the same. So let's check first if left and right are not the same. So if the left is not equal to the right, well, then we can actually double our count here. So we can do another result plus equals total count. Awesome. All right. But then we run into sort of the opposite problem. Now when we're going through our loops, let's say we have a root of 15 and we have 2 child nodes of a 3 and a 5. Well, first we'll check the 3. It will have a complement of 5 and we'll add all those nodes. Then we'll find the 5, it will have a complement of 3 and we'll add them again. We're going to double them. So I guess the problem that we run into is, well, maybe this isn't a problem. Maybe we can actually just not do this. So instead of doing this, we'll just let it go. We're actually doing extra work, but I think it's okay. All right, let's try this. I'm not 100% convinced. We might want to do that check, but let's give it a shot. Let's see if it works. Let's see, total count is not defined. Capital letter. Try this again. Okay, seems to work. Let's see if we can pass all the tests. This might be too slow, so actually let's preemptively add caching right here. Now you could do this with dynamic programming. I'm going to use caching because it's simple and easy, so let's just do that. Time limit exceeded. Okay, we passed 38 of our tests out of 40 something tests, so we actually do okay. Let's go back and let's do what we were initially planning to do here with our check. Let's see here. So if the left is not equal to right, then we know we basically have, we can mirror these nodes, the 2 child nodes. The left can become the right and vice versa. So that means we can just double the total count here. So let's just do this. We'll add another total count if left is not equal to right. But that does mean we have to keep track of which of these nodes we've already used, because once we use a left node and a right node, and we've doubled them up by mirroring them, we don't want to run across the right node, left node combination of those same nodes and double count them. So now we need to keep track of which nodes we visited. So let's do that here. We'll just have a visited set. So we'll have a set, and then as we go through our nodes, when we use a node, so in this case we're using both left and right here, we're just going to add them to our visited set. Now we might be able to save a little bit of time if we know that these are the same and just add them once. So we might be able to optimize this a little bit further. But we also do need to check now, have we used these nodes? Have we already visited these values before we get to this point? So if left in visited or right in visited, actually, we can do it a little bit easier. We only care about the left node, because if we visited one, we've had to visit the other. So let's do it here. If n is in visited, then we can continue. All right, that's easier. All right, if n's in visited, we'll continue. Otherwise, when we get to this point, we'll add both the left and the right to the visited. That way we don't end up double counting our mirrored child nodes. All right, let's run this. Still time limit exceeded. Oh man. Let's see, what can we do to speed this up? Because I think we're close, but just not quite there. All right. Well, one thing, I don't think we need this. So we can save a little bit with that check. All right. I always like putting the result first, so let's just do that. Okay, we still want our visited set. Get rid of this. All right, so if n is greater than or equal to root, yes, we'll still continue. If n is visited, we'll continue. All right, we have our left. Okay, so one thing, this might be a little bit slow. We're looking for some float in the array. Let's do an integer divide instead. But now we need to make sure that these two integers are actually going to multiply or result in our root, because we might be rounding down here. So let's do another check here. If left times right is not equal to root, then we'll continue. All right, so again, we're doing an integer divide, but that does mean we have to double check to make sure that these two have a product that is equal to the root. All right, then we'll check if right's not in the array. We'll continue if it's not. Then we'll add these to visited. I guess we maybe should speed this up a little bit. So, shoot. Well, let's just add them. It's fine. We'll add these to visited. All right. Let's see if that saves us enough. Okay, we're passing. All right. Let's submit this and see if we can pass all the tests. And we pass. We don't do very well though. In fact, we do pretty terribly. We're only at a 9% for runtime, 10% for runtime, and a 32% for memory. So not great. Now, there's a lot of ways we can speed this up. This was just the simple, straightforward way. So number one, this doesn't have to be a recursive function. If you note, really what we're doing is we're looking at nodes, or we're looking at values in our array and seeing whether or not we can create products of other nodes or other values in our array that equal that value. So we could just go through actually and multiply all of our values in the array together, looking to see if those values exist in the array. And then we could build up a cache of essentially all the different variations of these values. And then that would be our answer. So clearly this is not the most efficient way to do it. There are much better ways to do it, but this is kind of straightforward and easy to explain, just going recursive like this. See if there's anything else we could be doing. I don't know. There's no like super simple wins here. Yeah, I think for me, I'm going to have to leave it at that. I just don't have time to go into this. There could be a lot of refactoring we can do to make this a lot faster, but I'll leave that up to you. All right. Well, that's it for me. This has been LeetCode problem 823, binary trees with factors. It's been a medium problem. It's pretty medium. It's not too hard. It's not too easy. It's about right. All right. Well, that's it for me. I hope you enjoyed this. I hope you had fun. I hope you learned something, and I hope you can go out and write better code.